Okay, so now we have to talk about concepts. So let us try to see what a concept is. Okay, few introductions. Datum. What is a datum? It's a value. And that's a very difficult thing because, believe it or not, programming languages do not have values. We say, no, but I use values all the time. I'm sure Param thinks so, yes? But you don't. You use objects. Every value is someplace. There is no disembodied datums, right? But I just want to say that they are. They are. Whether they, we could refer to. The value is a datum together with interpretation. What's the meaning of this string 101? And I take, in some sense, if you like, very minimalistic, very simple view of the world. They're just zeros and ones, nothing else. So it's a value. You have to, you say, well, but it's obvious that 101 means 5. No, it is not. Nothing is ever obvious, right? Till you interpret. This is, of course, this is a normal, common interpretation. That's not the only interpretation. Another possible interpretation that it's -1. Why? Well, because, believe it or not, you say, I have 3-bit signed integers, and they're complement 1, they're not complement 2. This is a signed bit. 1 means negative. And this is 01 means 1. So, or sign magnitude, yes. Yes. Yeah. So, and now a value type. What is a value type? Value type is a set of values sharing common interpretation. Again, bits in the computer make no sense till we apply interpretation. Right? If you just look at the memory of the computer, you just see, pattern of zeros and ones which have no sense. You have to impose interpretation. You say, this means this means interpretation. Our heads, believe it or not. And again, this is interpretations of zeros and ones. So value has a type. Now, value types do not exist in programming languages. C++ or even Java. Ilya, hear that? Ilya is fully convinced that Java is very modern, advanced programming language where you could do everything. Well, you cannot talk about values because they do not exist. Objects exist. Right? Because again, this is not something, many evil things happen because people do not sit down and sort them in Aristotelian fashion, sort of classify them. So, but there are values. These are just interpreted sequences. Not in memory. They're just interpreted sequences. And object. What's an object? An object is some way of picking bits out of memory. You say they're consecutive bits. Not necessarily. There is some way, some, if you like, algorithm of picking ones and zeros out of memory. Okay? And it could be immutable or mutable. Because there is memory, this is the property of memory. Objects could change. And it could contain either all or some values of a value type. Right? But again, remember, it's not necessarily object. There is this naive view that object must be collocated bits. This is not the case. I mean, for anybody, by the way, in this advanced programming language, Java, just about nothing is collocated. It's all on the heap someplace far, far away. Or in C++, the most common thing called vector is not collocated. There is a header, and then there is the elements. They're not together. Bits are distributed. Some are on the wherever the header is, and then there is a heap allocated rest of the vector.
Alex, there was a time when people worked on strongly typed hardware.
Yes. For example, when they were building Burroughs machines. Yes.
And a few other machines where the actual type of the
yes, symbol machine, for example,
was stored with the
yes, with the tag. Yes.
So,
or list machine.
Yeah. So
yes.
What would that mean imply to your statement that we don't have? Would you say that that was storing an object, or
it was? No. I mean, you still store an object. It's an object. There is an address. Burroughs had addresses. List machine has locatives. You could modify them. Value is something. It does have interpretation. It does have type. What it doesn't have is location. It's, you know, you cannot even think about modifying. Number 2 is not modifiable. It's not because it's const. It's because values, any value is unmodifiable. It's
so the key point here is that it's not the lack of an interpretation that.
No. It's the value has interpretation. Then you sort of, I apologize if I didn't make it clear. Value is a datum, string of bits, together with its interpretation. Whether its interpretation is someplace in the compiler or someplace physically in the tag, or just in my mind. Of course, I mean, in my mind, people program in assembly language. I mean, they just write down on some piece of paper, this is this, and this is this, and this is this. I remember programming like that, but they still were values with an interpretation, right? Sort of, it's actually the primary interpretation, the interpretation, is in the mind. The fact that it gets into hardware too, you store bits. This is secondary, right? But again, sort of the value, the significant thing, it is just collection of zeros and one. Yes?
I'm not sure I understand where you're getting at with restrictive. Can you give me an example of something that's restricted but not immutable?
Yes. For example, if I attempt to implement integers, I'm restricted. I cannot really represent all the integers there are. There are just too many. However big computer you build, there still will be integers which are not representable. They're mutable. They're perfectly mutable. It could be 3 or 5. But it cannot be some huge big number which doesn't fit into memory. Just the simplest example is that sometimes I intend, and you say, well, but then it's limited. No, it's not limited. It's practically limited with this instantiation, sort of. In my conception, if you buy more memory, you could go further. These are big nums. Right? But in general, there are lots of examples of what cannot, when we represent things, we sort of, in computer science, we have to very often do this partial model. Like in mathematics, we have a theory in model, right? And which set of elements satisfy all the propositions. Not so in computer science. We have partial models where we say, well, we represent these elements and these operations. And when we go out, we just go out. There is no mapping. We live with that. We analyze, again, there is this book, which you might have heard, called Elements of Programming, which I recommend for many of you to many of you. If you read it, it deals in great detail with that. Right? But, and those of you who do not have a copy, welcome to come to my office and get a free copy. Please, please come. I still have lots of copies, and Paul and I were really depressed because none of you would. I mean, obviously, you're not going to read it, but at least you could try, out of politeness, to ask for it since it costs nothing. I don't know, but you could hide it if it's embarrassing, but whatever. I don't know what else. Next lecture, I'm going to stand on my knees. And by the end of the course, I'm going to do full prostrations, for those of you who know what it is. Things one has to do. So, back to Ilya. Java doesn't have it. So, no, I mean, he's a proud champion of Java. Nothing wrong. There is a great computer science, not great, very good computer science, or at least useful computer scientist called David Grease, good friend of Tom. And a few years back, he wrote an article in Computer. Computer is a magazine of IEEE Computer Society. And he wrote that we need to change the way we teach programming. And instead of using horrid things like C and C++, this is a direct quote, and starting with things like iteration and recursion, we should start educating programmers by teaching them inheritance in Java, inheritance and delegation. What? Oh, absolutely. I thought it was, Bjarne was visiting us when we got it. Bjarne was fuming, but he made my day. The core of programming is inheritance and delegation, not iteration and recursion. Gödel was spinning in his grave. So there was no inheritance in Gödel, just no inheritance. And in Turing, no inheritance or delegation. But Ilya, I'm not singling you out. You see, you always need a whipping boy. Occasionally I use Ryan and claim that he is a Presbyterian, which he denies. And, or Ilya, and I say that he invented Java, which he didn't. Guy still invented Java. No. Gosling invented Java. But somebody invented Java. Okay? So object time is a method of getting this value out of the address. Object always resides in an address. One address. You have to be able to point somewhere in memory, say where that's my thing is, a linked list. And then there is a method for getting all the elements of linked list. The value of linked list is just a sequence of elements, right? Abstract, disembodied. Couldn't do replugged. So, concepts. And here yes?
A lot of your definitions are sort of, it just depends on how people define certain words. I mean, in some sense.
That applies to any definition. Any definition depends.
A lot of your complaints has to do with just the fact that people define value differently, the word value.
No, what? No. And you do not understand what I'm saying. See, there is something I call value, and that is not referable to in modern programming languages. That's what I'm saying. It doesn't matter what I call it. You could call it foo. The concept of disembodied sequence of zeros and ones, which is interpreted like something. It does not exist, right? So, no, I'm not trying to argue words. I'm too old for that, right? So, now, concepts. And again, what we will observe, just since Ilya is going to attack me now and say, but you don't have to call concepts concepts. I don't. Why did I call them concepts? By the way, I was the guy, let me take credit for that. The guy who said, let's call concept. Concept was me. Because which choices did I have? If you go, I could point, it's provable, or Paul could attest, he probably even read my papers. I wanted to call them theories. What chances do you have to introduce theories to practical people who program in C++? I wanted to call them multi-sorted algebras. Do I have to continue? I want to call them algebraic structures. I did. I have papers. Right? And then after sort of realizing that it's not going to fly because there is this natural reaction of a practical programmer. If you say it's a multi-sorted algebra, he says he's a theoretician who lives in an ivory tower. He knows nothing about my search engine. Let him go away. I could introduce you to people like that. They do exist. So, therefore, I realized at some point that I have to come up with a word which doesn't sound mathematical, because mathematics is perceived as evil, not by me. And I came up with a good English word, concept, but it's exactly the same thing as a theory, right? Because I want to talk about things like groups and semi-groups. So concept. So what is a concept? People say, oh, concept, it is like an abstract class. No, it is not. Again, this is another thing. It's not I'm trying to be original or say that I'm clever. Just saying they do not exist in at least practical programming languages. One could argue they exist maybe in Haskell, but they do not exist in C++ or Java. What do I mean by that? Of course they do. Of course they do, in a sense. There are concepts. When you look, they're just not expressible in the language. Right? They're all over the place. Let us look at some concepts which are jump. And here I picked up concepts which, while written in C++ way, they of course originate with Java. There is a notion of an integral type. It is in Java, it is in C++. You just need to drop, I'm explaining to Ilya. If you drop _t, then you get Java. Right? With _t, it's C++. These people could never agree. So after Java did it this way, NCC had to do it differently because otherwise people say, oh, it looks like Java. So here they actually think Java way is better. This _t was unnecessary innovation. But in any case, the types, these things are in C++ and Java, yes? These things are not. They are conceptually, but they're not. You cannot say there is no way in the language to refer to an integral type or to unsigned integral type. You cannot. They just, right? So what does the thing concept mean? The concept means a collection of types. It's like genus. Like 5 is an individual. Right? Int is a species type. Concept is a genus. It's a collection of related types, not the same types. Related types, similar. Not with the same signatures, but with similar signatures. That is, there is this notion of similarity is very central to this. So these are integral concepts. And of course, sort of what is I'm trying to do for so many years, I'm trying to convince programmers that these things are. They're not just my invention. They actually exist. And you need to program in terms of concepts. So what do they mean? Sort of more formally, when we say that there is a concept of, say, integral, it is a predicate on a type. If you take a type, you could check, is it integral type? That's your broker, you have to answer. Apparently not. So the predicate, one type. So you could find out, and what does the predicate check? The predicate check, do they have the right operations? Do they have the right semantics? Do you have correct complexity? Here is a very important point on which there's another thing. What the number two thing on which I got grief, actually, that was not a grief in the sense of it didn't happen, but some of you might know that STL introduced complexity as a part of interface. And that was such a terrible experience because everybody, from practical programmers to very ivory tower people who specialize in abstract data types, everybody was unanimous. Alex, you just don't know anything. Complexity is a part of implementation. It's not part of the interface. It is so evident. You just, because, there is this paper by Parnas, you have to go read it, and any sort of attempts to say that I read the paper didn't work. This guy, Dave Parnas, he wrote the paper, you go and read the paper, and then you will know. What do I mean? What's an example? An example comes from sort of my favorite example. Once upon a time, there was commercial library, which they were selling for big bucks, which had abstract data types. And at that time, if you had a library with abstract data types, you had to have two abstract data types, because that's all the things people need, called stack and queue. I have to tell you that. When I did STL, STL had all kinds of things. What didn't it have? Stacks and queues. So Bjarne comes and says, oh, no, you have to put stacks and queues in. I say, you don't need to have stacks and queues because all the linear containers have push and pop operations. So pick the one you need. No. I mean, it's not going to fly. So I put this adapter, which takes a container, shadows all the operations instead of corresponding pushes and pops, and does either queue or stack or deck or whatever. And everybody is mollified, say, oh, he gets it. Back to our story. Look, life is such. There was this library. I think it was called Sabre. Some company in Boston was selling it for $50,000 for 5 people license. I mean, it's stack. And it was implemented by somebody very, very clever. So the way he implemented stack was like that. You have a stack was implemented like an array. And when you get an element, what do? It doesn't fit. So you relocate array from size n to size n plus 1. Put the element there. Yes. So they called it stack. It wasn't a stack. It wasn't anything humanly describable. Why? Because you see, it actually sort of, when you started, like for a while, it actually worked as a stack. But then it stopped working, just completely. It was quadratic. It would relocate, 10,000 elements for every insertion, or 10,001 and 10,002. So it was a dreadful thing. Nothing you could do. If you choose a bad thing, it will do bad thing. So how do you argue against people who say, but Dave Parnas wrote, whatever you wrote? You say that there is this invisible contract. People do not know anything, but they know stack supposed to be constant time insertion. That's what they expect. If a person knows what a stack is, not that formally, not he read the axioms, but his expectation, a programmer expectation, is that it is going to be constant time insertion. That's right. So complexity is the part of the interface, because the expectation of a programmer, if somebody says, I have a fully implemented search engine, you give a query, and it never returns. I mean, no, it returns, billion years from now. So is it a search engine? No, it's not a search engine. It's something else. Sort of complexity is a part of the interface. That was a very important sort of point. Still not well understood. So now, if we have concept as predicates on types, then we discover that there are other things which exist. And again, they do not exist because I want them, they are. Again, this is my constant argument. People say, Alex, you just want to invent something. No, I don't want to invent. I'm describing what is. And what I claim that we also have a notion of a type function. A function which takes type and returns type. Java doesn't have it. Neither does C++. Neither does, as far as I know, any I mean, the moment you go into research languages, you can find anything. But practically speaking, it's an unfamiliar thing. But obviously it exists, because if you have a type sequence, there is a type of elements in the sequence. How do you get from type sequence to type element? It's a function. It's a mapping. It's going from here to there. Right? Or if you have a polynomial, you have coefficients. Right? Or in a tuple, you could get first element type. It's a type function. I'm just saying that's what it is. And the remarkable thing, sort of, we belong somehow. There might be conservative communities. I don't know. But it seems that programmers are the most conservative people in the world. Because 20 years I have been talking about C++ needs type functions. It's trivial to put them in. Everybody says, no, we don't need them. There's no such thing. We still don't have them. This really, I mean, there were several rounds of standards of such a simple thing. And you say, well, it requires major language. No, it does not require any language innovation. I mean, paren is the only language. And, you know, you just say, this, you want to write this. Value type of sequence. And so you value type of whatever, vector of int. By the way, what is value type of vector of int? Int, yeah, good. So I mean, you want to do this, no syntax, absolutely no progress, and sort of violent resistance. It should have been there in the early 90s. Still not there. And then finally, if we have type functions, there's one more thing which you need. You could make type into type, but you actually could map type into something else, like a number. Which is, there is a thing called type attribute. And what it is like generalization of size of. We do have a type attribute in C. Java doesn't believe in things like that. But they're beyond size of everything. But alignment of. Try anybody who wrote any serious code knows that alignment is important. We cannot find it out. There is no way of finding how a particular thing is aligned. Again, over 20 years I have been arguing to the no more. You know, my sort of interaction with the language design community stopped, I forget, but I publicly announced there was a concept workshop here and I have witnesses. I stood up and said, guys, that's the last time I participate in any long language design activity. So I'm done, never again. So I rather read books about Aristotle. So more wisdom there. Alignment, you cannot find it out. But it is a type attribute. And whether we have it in the language, you need to know the concept of type attribute. Right? You need to learn to think in these terms, even if they're not doable. Or number of members in a struct. Is it difficult for a compiler to tell me that pair has two things? No. I mean, by the way, for both of these things, compiler has all the information, because you couldn't possibly compile the thing unless you know all this stuff. So just give it to me as a simple, you say, what's the syntax? Oh, that's the syntax. So is there a research issue? Yes. Do you have an underscore or not? Right? That's the only research issue. But that's an example of type attribute again. And of course, type attributes will remain. Whatever languages in Java, do they have type attribute? Of course they have type attribute. They don't know, but of course they do.
So in Java, reflection
allows you for some of the things to do that. Yes, this is true. No. Java, by the way, guys, Java is not an outright evil language. It's a mediocre language. It's a mediocre language. Because basically, sort of when people ask me that, why? Because some of you are old enough to remember Objective-C. That's the one I found. That's what Java is. It's basically this sort of an attempt to combine two worlds, the stack world for things like int and the heap world for things like that. And then there are multiple redressing of this idea. Sort of the idea of Objective-C was to make typed small talk with a stack on Java. He did that. Then some guys said, oh, we will do much better job because we will call this that. And they came, and then Microsoft, of course, came up with a totally identical language called C#, which great innovation is that it's the first language uses sharp sign. But, it's but fundamentally, it's an interesting idea, sort of take small talk and combine it with typing in this way. In this building, they invented modulo 3, and while I don't believe it is so, they claim it was like Java 2, and Java actually is derived from modulo 3. You could talk to Paul about it. He was one of the first users of modulo 3. So, notion of regular. And again, the notion of regular, the theory of regular things is not, people say, oh, this is C++. No, it is not C++. This is a universal notion, and what it means that there are certain types which allow you to do certain things. What do they allow you to do? They allow you to copy construct, a copy thing. And you say, copy, it's only C++. No. Xerox machines copy. Copy is not even a programming language concept. It's what does a copy mean? By the way, anybody knows what it means? To copy something? It's make something equal to the original. Right? This is why we need equality, because otherwise copy doesn't make sense. Because what does it mean to copy? You have to say what it means to be equal, to be able to copy. Otherwise, I could give you anything. Right? Assignment, again. Assignment is not particularly C++. Well, even Java has assignment, the last I heard. But so, copy, assignment, equality, destructor. Fundamental things. And there are fundamental axioms connecting them. Here, I could have written it in C++ like language, but I want to show that it actually is mathematics. What does construction mean? What does it mean that I construct A out of B? It means that for any C equal to B, it is going to be equal to the newly constructed thing. I'm really going to create a copy. I'm eliding certain issues which are deep. Copy has to be different from the original.
But it's not expressed.
It's not expressed. I'm eliding certain things, said I. I'm not saying, this is not a complete axiomatization, but this is something which shows you what construction must be. Again, this is unambiguous. Another argument, and now you see this, it's so wonderful to talk about Pythagoras and Aristotle. It's non-controversial. If you talk about modern things, everything becomes emotion. Because people say, oh, but I want to have a constructor which creates non-equal objects. I want to have a quality which multiplies two numbers, because I'm free. There should not be semantical constraints. This is path to perdition, guys. I mean, the reason you could create science is that you actually agree that certain things will mean certain things, that copy means copy. Equality means equality. Yes?
I have a question. Shouldn't these things be explained in the context of the fact that it does exist some, I don't know, support for them, like in the memory or something? Because otherwise, I mean, if you just write this, you mentioned briefly, but basically you want to create a new thing, right? You don't
Yes.
want the trivial equality that is behind that.
But I referred to that. That it has to be different. I didn't want to go into that. I know how to handle it, but it's just not something I want to handle in the course. It's sort of getting into theory of sort of different. There is a book you might have heard called Elements of Programming. So what could I say? This is, I'm trying to, one of the things which I'm doing, I'm trying to take this very dense book and put it into, very short, brief part of the course, because it's not a course on elements of programming. So, yes, you're right. I agree. But as I said, I lied it. I do not talk about it. I just show that copy means creating an equal object. That's what I'm trying to say. Assignment means, again, there is a deep connection between assignment and equality. And again, I know that it shouldn't be they should be distinct. You don't just point to the same thing. So, again, what does equality mean? Equality is extremely hard. Again, there is this book. So, but let me give you, this is basically, we need to go and get to sort of Leibniz definition of equality. So what does it mean that two things are equal? It means that any attributes, whatever observations we make on these things, are equal. But of course, it doesn't work in programming languages, because there is a function f, very simple function, which you use daily, which breaks that. Address of. So you need to say only for good functions. So you have to introduce the notion of regular function and say functions which sort of behave with certain, if you like, just values. They don't look at the addresses. That has to happen. And it's an axiom schema because it's for an arbitrary. Okay? And this is a non-constructive definition. If you want to know about construction definition, you have to read. Yes. So, semi-regular. Sometimes, some clever person comes and says, well, but I don't know how to write equality. Usually he's just lazy and we need to force him to write equality. Sometimes it's actually difficult to write equality. And there is, again, legitimate reasons, much less often than you think, not defining equality. What we do then is we introduce a concept of semi-regular, where what we say is that, of course, equality exists as Platonic equality, but it's not implemented. You cannot call it in your algorithm. So that's the notion of semi-regular type. So why does it have to exist as Platonic equality? Because otherwise copying makes no sense. I still have to say that somehow I'm copying, therefore creating an equal thing, equal but not identical. Right? So you still have to decide that. Again, I have to go fast. So if we do semi-regular, here finally we could come up with a practical algorithm. This is actually part of the standard. There is indeed an algorithm called swap, except it's inline. I didn't write inline. So you understand how it works. So this is the first algorithm for semi-regular, and indeed it requires all semi-regular operations. Why? Because it constructs, assigns, and destroys. You do not see the destructor, but the temp better go away. You expect it to go away. So if you like, it is the minimal algorithm for this theory. Right? Sort of, it uses all three things. At some point, long time ago, somebody asked me, sort of, how do I know that a programming language is good? I said a good programming language is a programming language which allows me to implement three things well, three things. And I don't mean operating system, compiler, and a database. I gave much easier examples. Swap, max, and linear search. The moment I could implement these three to my satisfaction, I'll be content. So far, I'm still looking. It is amazing that, so many years into programming language design, I still find issues with implementing these three. You understand what I mean? Max, find the largest element. Swap, something like that. And linear search. You say, but didn't you do it in STL? Yes. Did I do it to my satisfaction? No. For example, this semi-regular, there is no such word in C++. Of course, to compile this, you have to write sharp sign define semi-regular type name. Then it compiles. And then maybe 10 years from now, they'll introduce concepts, and you will be able to say semi-regular. But I'm not going to be around. You say, well, Alex, you're a young man. Aristotle died old, right? Distinguished, world famous. He was my age. So, at some point, I have to realize that I'm an old man. Paul doesn't realize it, but I have to. Iterator concepts. Finally, we get to where I'm heading. So, what are iterator concepts? And some of you heard of iterators. Well, since some of you actually write C++ code, you might have even used them. And people say, what are iterators? And some people, oh, Alex took pointers and blah, blah, blah. No, guys. Let me be quite honest. I knew about iterators before I knew C or C++. Where did I learn about iterators? From Peano. Iterators are theories with successor. Right? So it's my realization at some point that the successor operation going to the next is of fundamental nature, and there are gazillion algorithms which could be done in terms of that, where iterators came from. I'm just telling you how it is. And iterators, again, is a concept. Therefore, whether you realize it or not, they exist in C, Java. In Java, they have their notion of iterator, but whatever. I'm not even going to go there. But they exist. There is a notion. It's like a group. Iterator is a theory with successor. Except, unlike Peano successor, it's weaker. Remember, Peano successor is, for example, possesses the remarkable property, it's total. Iterators do not possess this property. They don't. I mean, they actually don't. You come to the end, and what's after that? The abyss. As with most functions in the computer, they're not total. They're partial functions. Right? Is it all right? No. We live with, we have to get accustomed to partial functions. Now, Peano tells us that if successors are equal, then predecessors are equal. No, guys. Iterators, or at least certain classes of iterators, do not have this property. Some of you know that pointers could point to the same thing. You could have two nodes, list nodes, actually sharing tails. Is it good? Look, it's not good, no bad. It's what you need to do. If you need to share tails, you share tails. Iterators still work, in spite of the fact that this Peano exists. And then Peano tells us that you cannot ever come back and have a loop. Let me tell you guys, you can. Because you can. It's just, there are data structures which go around. And there are very beautiful algorithms in a certain book, which tell you how to find whether there is a loop or not, and what's the size of the loop, and all of that. Second chapter, if you want to know, right in the beginning. So again, what is iterator? It's regular type operations, meaning you could copy it, you could compare them for equality. They're just regular. Yeah? Then we will see, sometimes we will. Then we have successor, and then there is an additional operation called dereferencing. Iterator points to a value. Iterator, as it were, is like a name. You see, there is Alex, and there is quote Alex, quote. The name and the thing. So iterator functions as also as a thing which allows you to get to something else, not itself, but something else. It could be dereferenced. So again, dereferencing. What do we assume about dereferencing? Well, we actually assume that it is fast. What do you mean fast? Fast. Well, it means that it is the fastest possible way of getting to this data. Because otherwise, you shouldn't be using this iterator. It's just a piece of junk. Right? If you should be using whatever, let's get to the data fast. Right? For example, if you have a linked list and somebody gives you an iterator to a linked list implemented as pointed to the beginning of the list and an index, it is not an iterator. It is not. I mean, you could get, I know how to write the code, but it will not be an iterator. Okay? There is another sort of way of putting it. Iterator is something which allows you to do linear search in linear time. Right? For example, the iterator I just described obviously will not allow you to do linear search in linear time. Linear search will become quadratic. So it has to be fast. Of course, they say there must be pointers because, no, they could be bigger. It's perfectly legitimate if they contain other data to allow for navigation for the successor. Right? But in some sense, if you have something there, some piece of data you want to get to, it has to be pretty much as fast as pointer. Again, there is a big argument between me and just about every implementer of STL. No, but safety is more important. I don't know what safety is, neither do they. But what they usually mean by let us also put a bunch of checks before we do the dereferencing to assure that you don't go to a bad place. Well, if I want to go to the bad place, I'll go there whether you put checks or not. I'm pretty clever, and most programmers are. That's the problem with them. So, they're dereferencing is fast. Then there are, of course, iterators which cannot be dereferenced. This is perfectly all right. First of all, they're past their n values. We'll talk about them shortly. And then there could be a singular value, like null pointer. Do not dereference null pointer. Nothing good will come out of it. Some people say, well, computers should automatically return 0. They're wrong. I mean, null pointer is a specific object which says, do not dereference me, I'm a bad pointer. Yes?
You know that Unix used to do that.
I know that Unix used to do it. I repeat, you should not dereference null pointer. I mean, you should not depend on sort of, yes. So singular values. So again, it's a partial function. But this is all right, by the way. Mathematicians never hesitate to define division.
Would that give you a total order if you allow a null dereference from successor to null?
This is a very, well, yes, of a very peculiar kind. It's null, 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 null forever. And of course, you could do many wonderful things.
No, null goes to 0 and 0 goes to 1.
No, it's a different operation. Plus successive versus dereferencing. No, it doesn't work like that. You should keep doing whatever you're doing, and then you're stuck with null. Dereference, 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 dereference. So whatever. No, it doesn't give you anything useful. It's a bad idea. So again, sort of what I'm just trying to say that you should try to use mathematical reasoning when you reason about even designing computers. So it's possible, as we do in AOP, to separate these two theories of dereferencing and successor. The idea is that it's very convenient if you could sort of assume that you could just use some STL algorithms without defining dereference. But again, I'm not going to go into this. And for those of you, very quickly, sort of, you could solve this problem. You cannot do it in C++ because for mysterious reason, this code is illegal and will become legal around the year 2040 when they finally realize what I'm talking about. So the idea is that if something is not an iterator, its meaning is itself. A name denotes something else. Not a name denotes itself. If I dereference 5, what should I get back? 5. A thing, philosophers talked about it for ages. But whatever. That's the illegal C++ implementation of what philosophers have been talking for ages. Ignore it. Okay. There are this remarkable connection, however, between dereferencing and successor, semantic connection. That dereferencing is possible whenever successor is defined, and the other way around. That is, if there is a step I could make, it means there is somebody who lives there. It doesn't mean that somebody lives everywhere. So I could come to the abyss, no more steps, nobody lives there. For those of you who know Lisp, there is this thing called nil. You would neither dereference it nor car it. Or for those of you who know C, there is this thing called null pointer. If eventually you get to a null pointer, you cannot you're at the end. Okay? So what does it mean? What's the significance? That if you have a range with values, of course, you might end up someplace where there's no value. But at least in the middle, if it's not non-empty range, there are values. You could be sure that you can do linear search. You could look down. Your machine is not going to melt. Okay? We will see. Okay? So forward iterators. What do we have? Equality, dereferencing, and successor, and all operations are constant time. All right? It's very simple. So what could you do? You could compare whether two positions are equal. You could make one step forward, and you could look down. You could look down unless you're at the end. If you reach the end, who knows? You might or might not be able to. I am not guaranteeing that you cannot look down. I am not guaranteeing that you can. Yes?
And why do you need equality?
Why do you need equality? Because otherwise it's very hard to find out when you get to the end.
But don't you need just a test that you are at the end, which is much weaker than the equality?
Yeah, okay, but think about every time people start thinking about what I recommend, look at natural models. So what is the test? I give you a position here in the list and there. What's the test? This is known as equality. If you do what you do, you will allow me to iterate to the end of the list. It's not what I want. I want to iterate to where I want to iterate. Where do I want to iterate? To some position. Position is the iterator, by the way, let me tell you. Another great regret is that iterators are called iterators. I never called them iterators. I detested the term iterator because these were heavyweight objects invented by some people which would contain all these operations. Right? But from my point of view, iterator was this very light thing which says position, points to the position. So the terms which I used in my published papers prior to STL were a position, B coordinate. It is a coordinate. It's where it is. And of course, when I propose this thing, they say, no, no, in C++, we call these things iterators. Of course, they didn't have anything like these things in C++. What they had is Michna idea of iterator, this heavyweight thing which contains the state, not the notion of just a position.
The heavyweight state can be more general. I mean, think of structures on which you don't have order, and you still can iterate on them.
Sure.
Like the pure set kind of thing.
Do. I don't know what it means, but do. Do. You see, I'm describing a theory. The beauty of, again, this is something which people do not quite grasp. Iterators are. There is some notorious Boost guy who always confused. He apparently invented STL. His name is Andrei Alexandrescu, John's good friend. And he writes and goes around giving iterators must go. Okay, the man has a limited understanding. There's a sharper way of saying it. What he doesn't understand, iterators are not something I invented. They are. There is a thing called pointer. It has certain semantics. There is a pointer into singly linked list. It has certain semantics. It's not my semantics. I do not impose. If you have some other theory, be my guest. There are many theories in mathematics. This is a theory of things which exist, commonly used by millions of programmers before I was born.
Well, there were very few programmers before you were.
But they used memory allocation. Von Neumann did. Yes, right? These things are, right? So there is this idea that we invent things. We don't. Only Alexandrescu invents things. In science, you do not invent. You discover what is and try to describe it. What I'm describing is these well-understood things, right? Which covers, you say you have things they do not cover. So do I. For example, if you want to deal with real numbers, by the way, much more important than your things, they are not iterators. There is no notion of successor. And equality is very difficult. Right? So there are useful things. I'm not doing a reduction. I'm not trying to say, let us do everything with iterators. What I'm saying, there is a huge classes of algorithms and data structures which possess this kind of iterators, just positions. Right? Which would just, you know, if you look at any code and old algorithms book, whatever algorithms book you had, you will see iterators in this code. Because you go through data structures, yeah, this is the pointer in the data structure. That's what it does. Especially for linear data structures, that's the kind of algorithms we have. So this is incorrect. Again, you have to start with reality, not with your great sort of, what's the problem with Boost crowd? Because they're also very clever. They invent the world. Instead of trying to see what is. Because they read science fiction. They don't read good books. It's all from Harry Potter. I have to blame Harry Potter. So look, guys, it's a very good discussion, but I didn't cover the material. So we'll cover it next time because I don't want to. But I'm not complaining. These are very good questions. It's actually for the first time you guys woke up. I mean, since the beginning of the course. In any case, we finally reached something. We will continue with this something. Okay? So see you next week.